Okay, so we're going to look at curve sketching. So the question simply says, sketch the curve y equals x minus 3 times by x squared plus 3x plus 6. Okay, so to sketch a curve, we need to know the behaviour of the function. Okay, so what sort of things can we look up? I might type this out actually. So we could find stationary points to find minimum and maximum. We could work out intercepts, so x-intercepts and y-intercepts. And something else we could do is asymptotes, if there are asymptotes, and behaviour for large values of x. Okay. Great. So that's what we're going to look at. Okay. So if we look at the curve to start with, we can very easily work out the x-intercepts, so where it crosses the x-axis. And we can do that by setting the function equal to 0, so we can say that x minus 3 times by x squared plus 3x plus 6 equals 0. Okay? Great. So when does this equal 0? So this equals 0 if x minus 3 equals 0, or if x squared plus 3x plus 6 equals 0. Okay? On the left hand side here we can just say, well, that's true when x equals 3. So x equals 3 is an x-intercept. Okay? What about here? Is this function ever equal to 0? It's a good question. And I don't think it is. I don't think it is. I think x squared plus 3x plus 6 looks like something like that. Okay, which means there will be no intercepts. Let's just think about that for a second. We could test that by, I know this won't factorise. I could try completing the square. So it's going to be minus 9 over 4 plus 6. Because that will be positive, when we take it over to the other side we'll get a negative, so there'll be no real roots. So this is not possible. Okay, so x equals 3 is our only x-intercept. What about y-intercept? Well, to find y-intercepts we can, I'll try x-intercept here. Okay, we're going to need to expand this bracket, I think. Or maybe not. Maybe not. We could just set x equal to 0. So when x equals 0, y equals, it's going to be 0 minus 3 for the first bracket, and the second bracket is going to be 0 squared plus 3 times 0 plus 6, so times by 6. So the y-intercept is going to be minus 18. Okay, I'm going to draw some axes here to help us look at the behaviour of this. Okay, I might make this longer as well. Okay, so what we know so far, we know that the x-intercept is 3. We know the y-intercept is minus 18. We know there's only one x-intercept. Great. So that's intercepts covered. Let's look at stationary points. So to find stationary points, what we're going to need to do is differentiate and set and find out when the gradient is 0. Okay, so we're going to need to expand the bracket now. So it's going to be y equals x cubed plus 3x squared plus 6x. For that I just did x times x squared, x times 3x, and x times 6. Now we can do minus 3x squared minus 9x minus 18. And it's clear when we expand the brackets that the y-intercept is going to be 18 as well. Okay, so that equals x cubed. The 3x squared and the minus 3x squared cancel out. So minus 3x minus 18. Great. So let's differentiate that now. So dy dx. That's going to be 3x squared minus 3. Lovely. So, what does that mean? Well, we want that equal to 0 because we're finding out when the gradient is 0. So this is for stationary points. So on that equals 0, we can say that 3x squared equals 3. So x squared, going to divide by 3 and square root it. It's going to be plus or minus 1. Okay. So that's the x value for the intercepts. So to find the y value, we're just going to plug these back into our function. Okay, so when x equals 0, or when x equals 1, sorry, y equals 1 cubed minus 3 minus 18. So that's going to be 1 minus 21. So that's minus 20. And then at x equals minus 1, we're going to have minus 1 plus 3 minus 18. So that's minus 19 plus 3. It's going to be minus 16. And does that make sense? I think so. Okay. Now you may think we need to determine whether these are minimum or maximum. We could, but we don't necessarily have to, because what we can also do is, having worked out the stationary points, we can work out the behaviour for large values of x, and actually for really small values of x. So let's look at as x tends to infinity, i.e. for very big values of x, what are our big values of x? So, well, if we look at our function here, when x gets really big, the dominant term is this x cubed term, okay? And that's positive. So as x gets bigger and bigger, this x cubed term is going to dominate, and y is going to get bigger and bigger. So as x tends to infinity, y tends to infinity. Okay. Now we also have to look at as x tends to minus infinity. So when x gets really, really negative. So when x gets more and more negative, this x cubed term is going to dominate again because it's going to be the largest value. And that means something that's negative cubed is also negative. So y is going to get smaller and smaller or more negative. So y is going to tend to minus infinity. Okay, so how does that relate to our graph? Well, I think for ease I'm going to move this stationary point and just change the axis. So it doesn't make a difference because I haven't drawn any points yet, but let's put all the information down that we've got. So we've got stationary points at 1 minus 20, so 1 is there, and minus 20 is there. We've also got a stationary point at minus 1, minus 16. Somewhere like, let's put it there. Okay. we know that for large values of x, y is also very big. So we know that it's going to go up here somewhere. We know that for really small values of x, y is also really small. It's going to be down here somewhere. Okay? So, y-intercept, large values of x. So we know it's going to cross the x-axis at 3. It's going to have a turning point here. Going to go through minus 18. Going to have another turning point here, and then for small values of x, going to get smaller and smaller. So that's x, that's y, and that's the function y equals x minus 3 times x squared plus 3x plus 6. Okay, and we didn't need to find the if these were minimum and maximum, because we could work them out through the behaviour for large values and small values of x. Great.